So I'm going to run through an exercise that I made up that covers really a lot of different UTAP wells. It primarily concentrates on NMR and fluid flow and combining those in sort of an example to show you the capabilities of both. What we're going to do is in your folder, you'll see if you just want to follow along with the steps that I'm taking, or if you want to repeat it afterwards, there's an NMR exercise with invasion PDF that you can follow. And then you should also have three LAS files.
You may want to share your screen.
Oh, sorry. I forgot that I didn't do that yet. Thanks, sorry. All right. Okay, so now my screen should be shared, and to show you the exercise, actually it's this one, in workshop materials for under NMR exercise files. I took out this workshop math that was just a pre-made math file, but you don't need it because we're going to actually remake it hopefully. And then you have the NMR exercise PDF, which is sort of the script that you can either use afterwards or try to follow along with us. And feel free to ask any questions along the way. And then there's three LAS files. We have a workshop logs LAS, T2 amplitude LAS, and then TCMR LAS. And so we're going to import all those. And one of them is a set of T2 amplitude displays that will use the NMR. We'll show you how UTAP Wells imports T2 distributions. Okay, so first thing, this one I can open it, although I have it printed out, so I'm going to probably be largely following my printed one, so I don't have to keep opening this up again. But you can see here, we're going to start off with one and two, importing the logs, and then setting up the tracks, and then using the NMR Studio, opening it up and starting to use the different tabs in that. We'll introduce you to that. So close this. So in UTAP wells, I'm going to start with a new well. And first thing I'm going to do is just import the regular logs. And so that is, go to the NMR exercises, and we're going to import the workshop logs. And import the TCMR logs. Okay. So now if we look in the tree, we should see those two logs in here. And now notice down below these in the well, there's a section for NMR data. And we don't have any yet, but we're going to import that now and show you how to import the NMR data. So now we can go back to the well, and we'll open the NMR Studio. And so the NMR Studio, we have all of the different things that you can do, put into tabs, and we kind of put them in the order that you'll usually do them. Although, you know, depending on what you're doing, the import and calculations are like two different ways of accessing initial data. But then we have some plots to view the data that you either create or import. And then usually you're going to want to do an inversion and then check the inversion analysis. And then after that, or sometimes before, you may want to do a simulation. And then we have some simulated log sets you can do. And then we have this, which I may talk about later, but it's pretty advanced. And so I don't know if it'll really be, it's a diffusion sensitivity contrast display. So what we're going to do first is we're going to go to the import tab. And so in here, you have two choices. You could import the data as a log set and then create NMR data set from it. But it's kind of like an extra step, and we can just skip that step by creating the NMR data directly from a file. And the difference is that since UTEP Wells, we primarily use LAS files rather than some of the, well, I'm not even sure what the standard now for the T2 distributions are. But the way that we import them is as a LAS file where we have different, we have the depths go down in the normal way for each log, and then each log is another time step. And so then what this does is it puts it together to create the distributions for each depth by putting together all the different logs. And if you want to actually see what that format looks like, we can look at it. Okay, I'm just going to find it in the workshop materials again. So it's this one here, and I'm going to open it up with Notepad, and we can just see. So it's a normal LAS file, except we use the LAS protocol has an option for making arrays where you put in brackets the number of the column for each next to each one. And so that allows software to put together all these logs as an array. And then what you see is the actual the depths are here in the first one. So at each depth, we have a log for each time step, or a value for each time step in the T2 distribution as a function of time. And so that's the format. This is a format that you need if you want to import T2 data. And then so then if you, let's see, make sure that we selected that. I forget if I did. T2 amplitude, okay. And then we can load that into the table. And notice that it brings up options because you may have several sets. In this case, we have the amp with 30 values and depth log with just one value, but you may have other ones. And I've seen some logs where they have many different sort of array values in here. And so the amp is the one that we want to pick with, it'll have 30 values. And then you can see those all show up in the, first of all, you see points per depth. So we said it had 30 values. And so that's 30 time steps. And if for some reason something was out of order, you could pick, you could change which one you want here. Or you could also manually set these time steps if you wanted to, if they weren't right. But what we recommend is that, first of all, you should pick the type of data that you've imported, so that way it knows how to create, what type of data to create in the NMR data. So in this case, it's going to be a parent T2. And then the software will look for a header that will contain like T2 min and T2 max. If it doesn't find something like that, okay. So down here you see you have options of you can set the data ranges for the different types of data. And if you have a header, then the values will show up here that it reads in the header. And you have the option of using that, or you can select or you can set the values for the type of data you selected. So in this case, we're picking T2, and T2A both use the same range. And so we're going to set this from 0.3 to 3000. That's in milliseconds. And all right, so now you see that when I set that, it updates the table, and now the times go from 0.3 logarithmically up to 3 milliseconds. And you also have the option to set magnetization. That's if you're actually importing decay curves. And so another thing that you can see here is that so this represents the times that you have for each depth. And if you want to see that what you put in makes sense or looks like what you're expecting, down here you can check, you can do a quick view at different depths. And this will show you, this will show you, I can pick any of the depths that were in the log, you know, 10,200 or something. We can see what the T2 looks like at that depth. You can see that it changes from depth to depth, and it looks basically as we would expect, and it's running from 0.3 to 3000 here. Or, well, can't quite see the end of it, but you can barely see it on here. Okay, so once we get that, we're not doing magnetization, so we don't need to give it a sequence to help it divide up a magnetization. And then in here, you can, if you want to import more than one, you may want to change the name of the data set that it's going to go to. In this case, we'll just leave it as NMR data, because we're just going to import this one data set. And so now that that's set up, we can just click import. It just verifies what you're going to import. And then if we click OK, then we can look in here. Now we see that we have NMR data, and we have T2A data. And for some reason, it's absolutely impossible to get my computer to stop turning off. Okay, so next thing we're going to do is to set up the tracks, and we're going to look at the data that we've imported. And the first goal that we have is to use the NMR Studio to try to set up the Earth model in order to reproduce the T2 data that we imported. So we're going to treat it sort of like any other logs that you import, where you want to try to match them with your Earth model simulation. So, so let's see, we're going to go to the track. All right, so in track 2, we're going to set up the boundaries and put the gamma ray in there. And eventually we're going to want both types of boundaries. So I'm just going to go ahead and add the petrophysical boundaries as well. And then we're going to go into the NMR workshop logs and get the gamma array. And we're going to set the, I'm going to set the modeling limit. So we have this here from 10,110 to 10,210. So we'll make this 100-foot range. So I'm going to go into here and set the modeling limits. Okay. And so that's the range we're interested in. So I'm going to zoom in on that. And then in the next one, we're going to import the resistivity. So I can just add plus here to add another track. And in this one, again, workshop logs. And we're going to import a deep and shallow resistivity. In this case, we have AHO 10 and AHO 90. And then we're going to make this logarithmic. And if you want, you can also put things like resistivity up as a title to look nicer. Go back to 2, we can put MRA. And then we'll add another one. And track 4, we're going to put the NMR or the neutron porosity and density. So pick this, make it go from 0 to 0.6. And then we'll pick the density. Make this go, oops, pick the density, rho Z. And we'll make this go from 1.65 to 2.65. And then we'll also add the PCMR here. We'll make this go the same as the okay. So that's our, we'll call this our density track.
Could you make it a little bigger so we can see the limits in the right too?
Okay.
The
Like
window?
this?
Yeah, exactly. Thank you.
Yeah. And then, okay, and then in the next one, we'll add the NMR. So the NMR, you just go over to, I mean, it says add NMR distribution, and it looks like a little NMR distribution. And if you click on it, you'll have choices of Earth model and field data. And the field data refers to what we saw in the tree under NMR, and so it has to be in there, not as a log in the well's log sets. So in this case, we want to look at the field data, And the data set name was NMR data, because that's what we set. Just has one shell, and it's T2A. And we know that it went from 0.3 to 3000, so we just have to adjust this to be 0.3 to start, and then have to add another decade in order to get it out to 3000. So now you can see up at the top where it says 0.3 to 3000. And if you want it to be more visible, you can change the height of these peaks just to make them look so you can see the shape easier, see some of the small ones. And then the last one we're going to put in is a like volume composition. So that's the very last thing icon here. I think it's one of the last things that we've added. Is this volume composition. So if you click that, then right now we haven't adjusted anything. So we just really have the raw values. And so now you should have something that looks basically like the picture in the exercise. And the next thing that we want to do is we need to make some boundaries so we can start populating some of these properties in more detail. Oh, wait, there's one more step that I skipped, step 4. I want to show you that, so even though we have some things that you can do even on imported data, it's sort of like log calculations, but in this case, it's for NMR. And if you go to the NMR Studio, toward the end here, we have this thing where you can create NMR log sets, and you have the choice of let me see. There it is. Okay, so you have the choice of different types. Either in here, there'll either be different data sets or there'll be the Earth model usually. We haven't created any Earth model data. So what you can do then is you pick the data set, and then in this case, we want to make a mean T2 because the log set didn't come with a mean T2, but it looks nice to have that on there. So we can create that from the data. And we'll just call it T2A, we'll call it data mean. And we'll assume, we'll just use stack 1, assuming that the data has already been stacked. And again, it'll be T2A. So then if we say create log sets, then we'll see. And by the way, if I didn't mention it yesterday, you can get, if you have something like this where you're using the well interpreter full window and you want to see something in the main window, you can go back and forth like this. And now we have a T2A data mean here with T2A LM with a shell and a level, stacking level. And so given that, we can then plot that here. So on top of the T2A distributions, we'll go to the simulated logs now because we simulated that, and T2A data mean. Okay, so we have that, and let's make it something a little brighter and thicker, maybe even thicker than that. And then we'll put it on top. So there you can see the T2A data mean that we can view on top of the T2A data that we imported. Oh, and then we also want to calculate the Earth model SW from the resistivity. So we're going to do that. Oops, oh, that's on the next step now, sorry. Yeah, okay, that's our starting point. So now 6, we want to make boundaries with the gamma ray. And you may want to, I mean, we can start with the gamma ray, but you know, you can use any log to make these boundaries. The gamma ray today is a little bit noisy, so let's see how it works. So logs, yeah. Okay, so first let's just see what happens if we just try it with the default settings. And it's actually not terrible. We may have a few extra. I'm just looking to see if there's any that we might want to get rid of or move. I think maybe I will. The thing is that, I mean, especially for an exercise for your own purposes, you may want to keep more, but for an exercise, it'll be easier if we have a few less logs, so, or a few less data points. So if something looks not too critical here, I'm gonna just remove it. I'll keep those 2. So I'm just gonna quickly run through and see if I see any others that look like they're not really contributing too much. And yeah, it's hard to say. So we have, I wanted to get it under, actually a bit smaller. So I'm going to try to, I'll get rid of one more here. And because actually, if you look here, like the resistivity is fairly neutral. So, and maybe this one up here. And we'll get rid of this one. And maybe this one. Okay. So I'll leave it like that. So we have somewhere around 47 layers. And we'll see in a minute the actual, I have a sort of a bad reason for wanting to reduce the layers, but we'll get to that. Okay, so now we have some layers. And so now we're going to use the log calculator, which I don't think we've actually talked about yet, but we're going to use it to calculate the CSH log. And then from that, we'll estimate some shale concentrations. So if you go over here on the top, you see several different, this will bring up the Log Studio, which I think in the new version is going to be broken up a little bit, but it allows you to do some calculations, either petrophysical calculations or custom log calculations or depth shifting and log filters. Look like that's the depth shift thing and custom calculations here. I think Joaquin did go over this a little bit. So up here in the shale concentration, we have several different shale calculation types you may recognize, the Clavier and Steiber and Arielnov and so forth. We're just going to stick with the linear, and we'll set it from 40 to 120, which this actually goes to 127 up here. So we should maybe have it a little bit higher. Go to 130. Okay, so then we can pick so you pick the log set you want to use, workshop logs, and we're going to use this gamma ray, and then we'll output the CSH calc into the same log set. Hit calculate. Once again, you can then look in the main window and see that we've now added into that CSH calc into that first log set. And you can do that with you can create a lot of new calculated logs that way. Okay, so so now we can plot this, and well, we'll use the populate properties to populate a few other properties, and then we'll plot them all in the tracks. So if we remember, we have this populate properties, and so we want to first we'll set up the resistivity, and we're doing this all in the formation. So we'll set up the resistivity, use a deep resistivity, and then we'll set up the shale porosity. We're just going to set a fixed value. So if you want to get something new that doesn't show up there, you can go in here, and most of them are under petrophysical, but there's might be a few that are in sonic or resistivity in particular. But in this case, we want the shale porosity, which is under porosity shale. And that one we're just setting as a fixed value, 0.15. We assume that maybe you measured that at some point. And then I'm going to give a total porosity. So we'll go back in here. And for that one, we'll use the TCMR. And then we want a, and we could actually, I've tried this with other times that I've done this one. We have other log calculators that you can do here to get maybe better porosities. For instance, it's not the log calculator. If you go to the log calculator, there's things like you can do shale correction for the density of neutron, and you can do density neutron averaging, and these things could possibly help you to get a better starting point for your porosity. But in this case, then we'll go to the shale concentration, and recall that we just created that log. So we'll select that. See, that shows up here, and these show up largely based on the units available. So it kind of scans all the logs and see which ones have similar units. And then finally, we want to set a water resistivity because we're going to calculate resistivity. So and I'm just looking for where the water resistivity is. It seems like I don't see it in there. I know it's around here somewhere.
It's in petrophysical, yeah.
Water, oh, there it is down at the bottom. Okay, I missed it somehow. Water resistivity, and we'll just set a value of 0.05. It's a little bit higher than you often see. Okay. So now we have all those things set, and now we can hit populate properties. So now those should be populated in our Earth model, and then we can calculate the nuclear. Well, we can actually, let's plot some of these. So in the first one, we'll plot the shale concentration. And that's an Earth model. So we're going to plot the Earth model properties. Well, we could show you the logs too, but black. And you can see that as we expect, it follows the gamma ray. And then we'll plot our porosity here. Yeah, we can just set the fraction to be the same as this one. And then, no, that's not what I wanted. Oh yeah, I want the track. Okay, so then I want to set the resistivity. Except I want that in 3. Earth model resistivity. Okay, so there we go. Okay. And then, so we've got those plotted. So then in the petrophysical calculator, we want to run the nuclear calculator. And we'll enforce the structure. And let's see, we can choose what order we want it to go in. And I think we'll put shell concentration a little bit lower, maybe make it look something like this. And then go ahead and hit calculate. Okay, and then if we plot the gamma ray for the Earth model in here, and we'll make that green like the other one, maybe a little thicker so we can see it easier. Okay, so we can see that in, oh wait, we got to make it the same range as well. So let's snap the API to API. So we see that in here, a lot of the gamma ray in the sand seems to be too low, and a lot of the gamma ray in the shale seems to be too high. So I'm going to show you some ways that you can adjust this that I think we haven't talked about yet using some of the other tools or preset settings that we have in UTEP Wells. So one of them is that you can adjust the, well, we did talk about the, we actually did talk about the palette, but one of the things that we can do here is to add some, so in order to increase the matrix gamma ray, we'll add something to it. So we'll add another component, and we'll put some muscovite in here, and we'll make it 10%. And then additionally, oh, okay, so we need to, basically we created a new composition here, and we want that to go everywhere. So we need to give it a name. So we'll call that sand. And then by giving this a name here, then we can go into the into the tracks, and we can set this everywhere. So entire modeling interval, we can set the mineral composition for the matrix, and notice that we made this new one and it's down at the bottom here. So this is the way that you can update your mineral compositions. And notice that now over here, I don't know why we have albite there, but we do have the muscovite. And so if we want to, we can put that up toward the top. Okay, and actually, yeah. And then the other thing is we saw that in the shale we had a little too much gamma ray, so we're going to reduce some of the values. And so the way that you can do that is if you go into the palette, you can actually access this from several different places. You can go into the palette, or we could get it from directly from the multi-well. But basically, we're going to go into the solid component database, and we'll see that we have values for. And by the way, if you go to this thing and you just want to see, oh, I just want to change the nuclear values, you can click this and it'll just show you the nuclear value. So you don't have to increase the window size or change everything. And so in this case, we want to change our shale, which is all illite, and we'll change that and reduce the potassium and thorium a little bit. So we'll make this 0.04. This 14 instead of 17. And so you can use this to change actually anything, or as Joaquin showed you yesterday, you can make new ones. And also you can show at the same time, you can show fluids if you want, go back and forth between fluids and solids. And you can show either just components in the Earth model, which is handy if you just want to see what you have that you might want to just change values for, or if you want to see all that you have available, then you can unclick that and you'll get all of them. Okay, so now we need to rerun the nuclear calculator and see if that updates things. Okay, so now you can see here that the Earth model gamma ray is a lot closer in many areas to the log that we imported. And I mean, you could play with this even more if you want to adjust it more. And this is just one way of adjusting that. So we're going to calculate, now we're going to calculate the Earth model water saturation. From resistivity, and we're going to plot that. And so first, oh wait, I don't want to put that in here. We'll put that over here. Make it a bright blue. And I'll move that up. 0 to 1. Okay. And so there's our water saturation currently. And now we're going to go to the petrophysical calculator. And for this, we're going to, we want to update both the water resistivity, because we had set, actually, no, we don't want to update that because we set a value for that already. Yeah, so we're just going to use Archie's, and we're going to get water saturation from resistivities. And we can actually turn off these if we want. and then calculate. Okay. And so now we see that it's very high in these places and low in the center here. I think sometimes, you know, this is of course dependent also on the exact number of layers that you had in for instance, the porosity. So some of these values, you will sometimes see different ones depending where you put the layers, because then that will decide where the porosity values are going to be selected, as far as where the peaks and valleys are, and then that'll determine, again, what your water saturation would be relative to the resistivity. So in here especially, you see a lot of variation in the water saturation, even though the resistivity is roughly the same, but that's because we have all this variation up here in the porosity. Okay, so then the next thing we want to do is we're going to start working on, you can see that we more or less have a populated Earth model now. We have our water and mineral components and so forth. And so now we're going to try to calculate we want to try to match, see what we need to update in order to simulate this NMR input. And so we're going to go to the NMR Studio. And so the NMR is one of the more, I hesitate to say one of the more complicated, because really if you get into it, a lot of our modules are kind of complicated, but we try to make them have easy defaults to use. So, but you know, like the MCMC or the PCKR, there's a lot of options that you can do. You can either accept the defaults, or you can really modify it to your heart's content. So in here, as I said, we have these different tabs that I mentioned. So you already saw the import tab. We'll look at the plots tab in a bit and the rest of these. So I'm going to concentrate on the Earth model calculations, because this is the first thing you have to do. And I think a lot of people, if you're not used to UTAP wells or doing simulations, you may not, sometimes people get confused about what they have to change. I mentioned this yesterday when I was talking about the nuclear. We have that button on the nuclear to make sure that you update the nuclear calculator before you run the simulations, because the simulations are always run on the Earth model. And if you don't have your Earth model updated to the values that you want, your simulations are not going to give you the right values. And so that was the case. So in the case of the nuclear, you run nuclear simulations, for instance, on the thorium and potassium, uranium, PEF, but those are calculated from the SNUPAR or from the UT NuPro, which creates the values in the Earth model based on the minerals and so forth that you have set. And so that's similar for NMR. We have the simulator down here, and the simulator will take your Earth model and it'll decide what the effects of layer nearby layers are, or the effects of invasion or different things like that, or just the effects of the tool tool resolution. But in order for any of that to work, you first have to have values in your Earth model. And so that's what the EM calculator does. It calculates values in the Earth model that you can then run the simulations on, or in some cases the inversion on. And there's two types here. One is the relaxivity domain. And what that means is it basically it's what we used to have. It's the only thing we used to have. And it sort of creates distributions like T2 distributions or diffusion distributions based on what you have set in your components. And so in the components, if you go to NMR, you see that you have set for each component, you have a T2 bulk and mean and a T2 bulk standard deviation, and same with T1 and same with D. And then you also have the phase here. But if you use a relaxivity domain, it just takes, basically it just takes these values here and it says, okay, you know, we have T2 bulk is 1500 with a standard deviation of 150, and it'll just create a curve that has this mean and standard deviation. And it doesn't take into account really anything else in the Earth model very much. Whereas if you do a time domain, this one actually creates decay curves, and so you'll see that it takes into account a lot of it takes into account everything in the Earth model, as well as all your rock classes. We have actually, if you open up the NMR rock class, we have a set of distributions that depend on the pore radius. So down at the bottom here, you can see the pore radius, and we have actually, I think, 1, 2, 3, 4, 5, 6, 7 distributions here that you can modify based on pore radius. So they include, for instance, you can have a pore size dependent water saturation. Well, first of all, you can have a multimodal distribution up here if you want, by adding different distributions, and then you can have a pore size dependent shape function. So if you want pores that are small to be spherical and large to be cylindrical or something like that, you can do that. We have surface water contact, which basically generates your wetting. So it says how much of the pore space is in contact with water, or how much of the pore surface is in contact with water, and that will give you your wetting index.
You have a question, Bruce.
Oh,
in the chat.
How does the unknown oil-based mud affect the distribution from the model? Unknown oil-based mud. So I'm not sure exactly what you mean by unknown. If you're referring to what we show in here. So you can select, I mean, typically the mud will have no effect. But but if you have a non-uniform, well, and certainly for the Earth model calculation, it'll have no effect. In the simulation, it will take into account if you have changes in your borehole size. Like for instance, if you have a washout or something, it will run the tool down the borehole, and if there's a washout within the length of the tool, then those layers will be to the depth of that washout will be filled with whatever mud composition you have here, and then those values will get taken into account in the total simulated calculation. But typically, I mean, it would have to be deeper than an inch or deeper than 1.5 inches for you to probably see it. But yeah, in general, And I mean, that's assuming that you're talking about mud in the borehole, which I think maybe you're not. Unknown oil-based mud effect and distribution from the model. So if you're talking about instead invasion, then I mean that's comes later. But I mean, the invaded fluid will affect it like any other fluid. It's just it'll be part of the fluid composition in each section of the Earth model, and that will get taken into account by the calculations and by the simulator. Can we estimate TW for a model pore distribution? Model pore distribution. I don't know that. You can, let's see. I'm not sure exactly how they're, what the relationship would be. I mean, you can certainly run them for different pore distributions if that's what you mean. But yeah, if you mean in order to see the effect, because it's gonna, I mean, the pore distribution is just one of the effects that's going to affect your T1. And so I'm not sure how that it would directly be able to, that you'd directly be able to calculate
allow
that.
me to clarify the question, maybe that wasn't clear enough. So basically, sometimes like we notice that we have like a porosity undercalling within MR, and we kind of figure out that the TW is not sufficient. Basically, we need to wait more to basically activate or magnetize all the pore space, especially when we talk about like micropore, etc. So is there any way to inverse the process and kind of start from pore model and try to figure out how much would be the minimum TW we need?
I mean, there's a brute force way, which is especially if you have scripting. I mean, you could run this a whole bunch of times and change the TW in your sequence and then see when it shows up. But as far as, I mean, how to calculate it just in a simple calculation, I'm not sure that I know how to do that, because I think it might be more complicated than just the pore distribution. But I guess what I would say is that's a kind of a question that this should allow you to ask from a test. I mean, from a point of view of simulation or analysis, where you can try, you can model basically different cases and see what the results are, without having to actually run anything in the hole. And I mean, but you would have to have like all the other values, the different T1 and relaxivity values and things set in the right components and things like that in order to get a correct value. Yeah, so that's I guess all I can say about that. I'm not aware of how you would estimate the T1 directly from a pore size distribution. So anyway, we're going to look at these distributions a little bit more later, but I just wanted to show you those. And so those, so the rock class is accessible directly from here if you want to. And probably a lot of times, if you're going to run a calculation, you may want to, and we will later, access the rock class quickly and update different values and maybe add new rock classes and so forth. And then so this one just sets the layers that you're going to run, and this will probably be changing in a new version because we have a simpler, more central way of setting the layers, but you can use this. And then the component editors I showed you, we'll bring up the component editor quickly. And then so you can either calculate the time domain or the relaxivity domain or both. And today we're just going to do time domain. So we're going to basically calculate for each section of the Earth model decay curve, or potentially a set of decay curves. And then the DOI is useful, especially after you run like a fluid flow where you create a lot of very deep invasion zones, and NMR will not see them, so there's no point in really calculating them or simulating them. And so you can apply the DOI, and that will just do all the calculations out to whatever level you set, whatever depth you set here. And since in the case of our simulators, we only go out to 4.5 inches. We have 3 shells, 1.5 inches, 2.5 inches, and I think it's actually 4 inches, not 4.5. I would have to check. And then, and so there's not really much point in calculating out beyond that. And then you can add some noise here if you want, which what it really does is it creates a separate noise channel that you can then add or remove from the clean Earth model calculation. And then if you have a non-uniform borehole, like you applied a caliper or something to it, you could set your mud in here, and it will calculate the those small mud effects, or it will calculate in the Earth model some layers for that mud, and then you can set the CW if you're using water. The domain settings are for relaxivity only, so they won't affect us today. What will affect us is the thing with the time domain is that you can create your own sequences, or you can use actual sequences, and you can, if you want, you can create new ones, and we will after we try this first one. So this is a default sequence, so that's what we're going to run first, and we're just going to see what that looks like. So we can go ahead and click calculate, and it shows you that it's calculating it for all the layers, and we just have the one zone, so it just calculates zone 2. And then if you want to see those, we can go to the 1D plots, and notice here that we have 3 types of data. You have the Earth model data, which is what we just calculated. You have field data, which is what we imported. And then you have simulated data, which is what we may, or I mean, in this case, we will generate very soon. And so right now we have Earth model and field data. And if we click, so if we, for instance, if you click field data, we can pick some value and T2A. And okay, so there's one of our field data, and we can pick as many data points as we want and plot these in the partial porosity plots. But if we check Earth model, we know that we didn't calculate any relaxivity data, but we did calculate some time domain data. So then we need to pick some layers. You can just set all to look at all layers. We should only have one. Well, we have, it does calculate the borehole, but we don't need it for anything. So we calculate this, and in this case, we only have the one sequence. But now, of course, you don't see anything in the partial porosity here because we don't have any partial porosity plots in the Earth model right now. But we did calculate decays. So if you go to the decay plot or the magnetization decays, then you can see these are all of the Earth model magnetization decays for all the different layers that we calculated. And right now we don't have any sim data. And we'll go back and forth to this to see how the other data shows up. Okay, so then now there's different ways that we can simulate this. So right now this is what we have in the Earth model. We have these decays. And in the simulator, there's really four different types of simulations you can do. And the first two have the data source so the relaxivity domain we didn't calculate that, but the time domain and the relaxivity domain are two different types of NMR data, as I kind of described, that you can have in the Earth model. And we only calculated time domain data. But then for each of those, you can have either distributions or you can have decays. So for instance, we can calculate time domain data and then invert it, in which case the Earth model would have relaxivity domain data in the time domain source. But in this case, right now, it only has the decay curve. So we're going to be simulating the time domain source with time domain data, so the decay curves. And let's see if I say what sampling rate I want. Yeah, we're going to do a 0.5 foot step. And we're going to add a little bit of noise to this. Show you, and because it always says it works better with noise. And so the first one, we can just leave it as NMR simulation. So now realize that when we simulate this, we're simulating the effect that that our layers and so forth in our tool resolution will have on the decay curves. But we still, I mean, if we want to get distributions, we will still have to invert those decay curves. The question is whether you invert the ones that are directly calculated in the Earth model or whether you want to invert the simulated ones. And so the most in-depth process is to create time domain data in the Earth model, simulate the time domain data, and then invert that. And that's most like what you do in the field. So we'll simulate that, and then, and now if we go to the 1D, we should have simulated data. And another thing you can do here, we have match Earth model layers if you want to, because usually simulations and data will have many more depths than what you calculate, than the layers that you have in the Earth model. And so rather than see every depth, you might just want to see the center value at each depth and compare that to the Earth model values. And so we can click this and it'll automatically select the center value at each depth. And then, and so now we can see the simulated data. That's the simulated data. And it's just slightly different from the Earth model data. And you can compare them. I mean, it might be easier if you just want to see the effect that the simulation has on a particular layer, then you can just select that particular layer. And now the next step is we're going to invert this. And so to invert this, so we're not going to invert the Earth model data directly. As I said, we have the distributions in the Earth model, but we did a simulation. So we want to do so now, and maybe I should point this out, that because we did that simulation, we now have another NMR data set. So if you go to the main window, we now have another NMR data set. You see this one, the first one had T2A data distributions, and the second one has decay data. Right now, it just has decay data, but when we want to invert this to also get T2A distributions. So in this case, so we select that NMR data set, the NMR simulation, select the sequence that we want. We're going to invert all depths, and since we don't have any invasion, we'll just invert for shell 3, and for now we'll leave it at stack 1. And then there's a lot of solver options here. Depending on which sequence type you pick, different ones will be available. For the basic sequence, don't have many different kernels or methods, but you do have some option in solvers if you want. Basically, you can try different things if something doesn't look right or doesn't seem to be working right. Some of them are faster and slower than others. And I don't know, it's talking to Mohammed, it's very complicated to figure out if you make really complicated sequences, which kernel or which solver exactly to use. But that's something, if you start working with really complicated sequences, you may want to play with. The one thing I will say about it is that the kernels that you pick will affect the time of the inversion. And so there's usually a default inversion domain. And the main thing is the number of points. And so for some very difficult inversions, it will pick many less points just because it takes so long and uses up so much memory. So for instance, if you start doing some 3D inversions, it may be down to like 20 points or something that it recommends, because otherwise it can overload your computer. Then over here we have compression. So you can either have no compression or SVD or Windows Sum. Our default is the SVD. And then you have regularization, which you can use S-curve or discrepancy principle. And it really calculates both. But you say which one you want it to try to use first. If that one doesn't work, it's going to pick the other one anyway. In the case of if you're using Tikhonov model, you can pick what order you want. And then down here, as I said, you have, depending on what type of inversion you're doing, you have you can set your domain settings. In our case, we want to set custom because we're going to try to match the our input log. But your domain will affect the results that you get, and you want to be sure that it's big enough to cover the different peaks that you'll have. And then now the parameters or range settings. This has to do with your regularization range and the number of points. And if you what this does, if you pick the default, you'll see that these are grayed out, and that's because it's going to calculate, it's going to try different regularizations between, in this case, 0.01 and 100, and it'll do 51 calculations, and then it'll try to pick based on what you picked as the regularization mode, it will try to pick the best one. And And so we'll try this first, but a lot of times you may want to change this, or you may want to use what you see in the inversion analysis to pick your own and then just set that. And so if you pick custom, then these are available, and you see that the number of points goes to 1, and whatever you set in the minimum will be the value that it uses, because it just starts with the first point. So first we'll see what we get with the default. And we're going to put this in the same data set name, NMR simulation. And then if we go to, so first if we go to the main window, now you see there's a T2A distribution in the NMR simulation. So we took those decays from the Earth model, we simulated them, and then we inverted those simulated decays to get T2 distributions. Okay, so now you can look at those now if you want in the plots. And so now we have both the field and the simulated data showing in the plots. So we need simulation. This should be showing up. Maybe I can hit T2A. That should be, that's actually what comes out. Okay, I'm not sure why my simulated is not showing here. Oh, okay. It's just got a much smaller scale than the field data that we had. Okay, so that's the simulated data. And this is mostly useful if you want to look at, one or a few layers at a time. But instead, we're going to.
So David is trying to load. Look at the questions.
In the NMR,
trying to load the default sequence.
Load the default sequence?
I got lost a ways back. Something froze up and I had to restart the project, so I'm way behind. But this is from step 11.
Step 11. Yeah, you don't have to load it. It's like the default is already there because it's a default. So you just have to look.
In the wrong box.
You just have to look at it. What you do have to do is make sure that you just select time domain.
Yeah.
And set your DOI should already be defaulted. In our case, we added some noise, and that's basically all we did so far in here. I showed you some other things, but then you can just calculate, and the calculation should be fairly quick. And then when you simulate, you do the time domain, and then put some small amount of noise, like 0.005.
Yeah.
And then you can simulate it. And also I used a 0.5 sampling rate.
Yeah.
And then
okay.
and then in the inversion, if you need help setting, and these were mostly default too. The only thing I changed was the domain settings, where I made it the same as our imported data. Well, the number of points is different, but the and so one thing I didn't show is we also have an inversion analysis, and this is where you can see what it did, how it picked its regularization, and you can pick either all or a few of the depths, and not sure why. So 3. there we go. I guess it was taking a while to plot them. Okay, and so here it's again maybe more useful if you just look at a few of them. But you can see up here it calculates the S curve and the discrepancy principal curve, and then we said discrepancy principal, but it looked at that and it didn't find a good value there for some reason, and so then it went ahead with the, or no, actually, I guess it did use the S curve, but it picked 1.2, which is fairly low. Or, I mean, it's not super low, but it's a lot of times it'll pick a higher one when we have the noise. So what you can do here sometimes is to just, I mean, one problem is there's so many depths. I think it takes a long time to populate the selector. And well, I was waiting for the selector to come up. Yeah, it seems to be slowing down for something. So yeah, we can set none and just pick a couple of these. I think if you pick too many, it just, I'm not sure why this one seems to take a lot more effort. So what you can see here then is you can see how well the inverted, it calculates the decay curves from the inverted curves, and you can see how well they fit then. And a lot of times you'll see, like, in some cases, they'll start to get a little bit off. A lot of times in the lower, especially in the lower time decay regions. But this one, it looks like we have a good fit. And so then we can plot this and see what it looks like compared to our imported one. So we'll make a new NMR track. And I'm going to add NMR distribution. And in this case, we're going to look at the simulated data shelf. And yeah, so these are the, and here it says shell, but rather than giving the number, it actually gives the depth. So it's the 1.5 inch depth or the 2.5 or the 4 inch depth. And then T2A. So we need 4 decades and set this at 0.3. Okay, so now we matched up the range, the domains, and now we just want to increase this size so we can, it looks like they're more on the same scale. Whoops, what was that? Oh, hit the wrong one. This size. All right, so now in the script, we kind of ask what looks wrong with this. So these should be on the same scale. And we see a number of things. One of them, it looks like our oil peak is kind of too high. It's too skinny. It doesn't look very, it looks pretty homogeneous. I mean, except for the amount, the heights. Over here, it looks like our, what we might assume is either the shale or the water peak. I think it's the shale peak, seems to be much too high. And then in here where we have more sand, we see that this it's fairly homogeneous, but we'll have to wait and see if it's a little hard to tell right now if we want to adjust anything to move these peaks. But what we're going to look at next is how can we make this look more like the input, the imported data. And okay, so what we're going to do first is we're going to change the sequence a little bit. And so open this up and we're going to go to the EM calculations, and now we're going to add a new sequence. So you can make your own sequences. You can give this any name you want. I mean, actually, I guess maybe default to, actually, well, we're making it from default, so I'll leave it as default to. And in order to make this more realistic, we assume that we know the from the information we're given from the service company what the parameters are for the NMR scan, and so we're going to set this to 0.2 for the TES, and then this we just have 3,000 points. I don't know why that changed. Okay, so so we're just gonna lower the TES, and so one thing that you might notice right away is we have less points and we have a smaller TES, so we would expect that the maximum time decay time we can see is going to be much smaller here, and so we'll see what effect that has. Okay, so now we'll compare this to the new distribution. So we're going to calculate this. Okay, and then we'll just run through the same sequence where we will simulate it. And well, I don't think we could, I mean, it'll be easy to see what the difference is, so we don't need to make a new simulation. We'll just overwrite it. But it's one case where if you wanted to, you could make another simulation. You could go back and forth from the initial one to the old one if you wanted to see what the two different sequences look like side by side. And then we need to re-invert this one. And again, this would be also, I mean, another advantage to using a custom is that it doesn't have to take these 51 points to try to find the maximum. So if you are happy with, or like you think you know what regularization you want to use, you can just pick that and use custom, and then it'll just go a little bit faster, which in some cases can be important. Okay, so now we should have that done. We can check our inversion analysis. I think, did I invert it? Yeah, I did. Okay. Maybe I didn't. This doesn't look right. I don't actually see much change there. I feel like something I missed. Let me see, maybe I got distracted and missed a step here. Okay, we did the calculation. Oh, I checked both of these. Okay, I have to uncheck because if we do both of them, then we have the two sequences. And yeah, so hopefully we'll just have the one. And let's try this. It should overwrite what was in there before in our simulator. Oh, okay. Yeah, that's what I forgot. You got to be sure, because we made a new sequence, you got to be sure to select that here. And then same thing. Well, yeah, here we have to be sure that the new one is the one that's selected. Default 2, and the rest of this we can keep the same. And let's invert that now. So one thing we can notice right away here is if we just plot these now, the simulated data. Let me turn off the Earth model for a second. So if we plot the simulated decay curves, we see that before they all kind of went down to 0 at the maximum, but now they're not really going down to 0 anymore. And so this could be a problem because now we're missing some of this long time data. And so now if we close this and, okay, so now you can see the effect this has. So we end up with these curves are spread out a little bit more, and they have some what I would call some tails on them. And over here, I mean, they actually not only does it seem to have increased the peak, but it's actually run these off at the long time range. They actually run off the graph, and so. And now part of that might be good because if we're trying to match this, we see that this one also runs off, probably for the same reason. But in this case, this might mean that we need to adjust some of our Earth model parameters. So now we're going to start updating some NMR parameters to try to make this match up better. And let's see. I don't know if anybody, should we take a break or just keep going?
Maybe let's take a short break if there's no.
Okay, we've been going for like an hour and a half. Let's take a little break here. Let me check what the schedule is.
Hey, Bruce.
Oh,
How did you display the partial porosity plots to go from, cause I'm showing like 0 to like 1200.
these or in the studio or where? Or I'm
In
not sure what.
in the NMR studio, under
Uh-huh.
plots 1D.
Uh-huh.
How did you get those partial porosity plots to show up?
Did you, so you simulated the data
Yes.
and you picked the NMR simulation and you have a set, have a set of MD values here. And then you pick shell 3. So did you pick T2A? That's usually the one that people forget.
Yeah, but mine is showing, you see how your y-axis is going from 0 to 0.02? Mine goes as high as 1200. I'm kind of, and it's just showing one T2 display. Or do I need to,
Um,
maybe it's because I have
Did
both.
you have, did you uncheck these other two?
Yeah, let me do that and see. Oh, okay. Now it shows up. Okay.
Yeah, the field data has a much higher, so it totally throws off the scale when it plots it. Because for some reason the field data has a much higher partial porosity.
Okay, thank you.